How's everybody doing? Have a good morning so far? Does anybody have class before this? Can you guys hear me? Okay, good. I was concerned. All right, it's 9:55. Let's get started. Lord, thank you for bringing us together this morning, and thank you for the promise of the upcoming weekend. I pray that you would help us to manage our time appropriately so that we can not just do work, but also rest and enjoy the weekend. Pray that you would help everybody get moved in safely if they're not back on campus yet. Help them to get prepared for next week and help us hit the ground running when we get started. In your name we pray. Amen. Okay. All right. So, um, somebody, just one person, just keeps not doing that poll. So we're gonna end the poll. We're gonna talk about it. Most of you guys are here. One of you is not here, and one person doesn't understand the question, which I get, right? Because existence is a tricky thing, right? Are we any of us here? How do we know, right? These are these are the deep questions that keep me awake at night, right? So there you go. That's what it looks like. Great, awesome, fantastic. What are we doing today, right? What are we doing today? Well, we're going to recap last class. We're going to talk about electromechanical systems, right? So last time we focused solely on electrical systems. This time we're going to see what happens when we put when an electrical system and a mechanical system love each other very much, and then right we get some example problems, right? So that's what we're working on. All right. Let's see here. What do we got? Amps. Um, Apparently, you guys think that Kirchhoff's laws are overpowered, right? That's what OP means. Overpowered. Yeah. Yeah. Cool. So you're right. They are overpowered, right? They do everything for electrical systems. All right. So you guys are confused about op amps. I'm going to table that for a second because we're gonna recap op amps in a second. If you're still confused at the end of class, we can talk about them more. But we're gonna watch a video. Um, that uh, should hopefully help with that. Okay. Um, Kirchhoff, mathematical truths, op amps, parallel, trust the process, confusion. Um, I think parallel versus series. How do we handle things in parallel versus in series, right? Um, well, if you don't have, as of right now, so later when we get to Laplace transforms, we're going to learn about something called impedance. And the impedance method will allow us to do some really cool stuff, but we're not there yet. So you can't add two unlike elements that are in series, right? Like if I have a resistor in series with a capacitance, I can't add those together. You can only add things together that are, two resistors, three resistors, right? That's how we combine them. And why do we want to do that? Just so we don't have to handle all the different voltage drops and things like that, right? We can solidify one voltage drop across all of our elements. And well, if we had one equivalent resistor of this size, we would get the same response, right? That's what the whole point of bringing things together is. Parallel are when the paths are parallel, and series are when they're connected in line, right? We're gonna do more examples, right? I've been saying this too. The best way to increase your knowledge about things is to try problems, right? So we're going to do examples in class, and then we are. Then if you have questions, you ask questions, right? And we'll go from there, right? Come to office hours with any questions that don't get answered in class. Make sure you're getting your questions answered. I think most of the stuff comes around, most of the confusion probably comes around when do we use voltage law versus when do we use the current law, right? How do you know? How do you know which one you're going to need? Well, if you don't have any nodes in a circuit, if you have a simple RL circuit like we had in our very first example, right, that we did, there's no nodes, right? So if you don't have a node, then KCL is not going to get you anything that's interesting, right? And so KVL is there, right? So I guess the general rule of thumb would be see if you have a node. If you have a node, then you can use KCL. If you don't have a node, then don't bother with it. When can you use KVL? Anytime that you have a closed loop. So how do I know which one to use? Do I always need to use both? More often than not in complex circuits, you're going to need to use some combination of the two, right? Because the way that we're doing this analysis is we're getting everything in terms of either the voltage drop across the capacitor or the current through the inductor, right? That's what we are getting our model for. Remember, we're only using E sub C and I sub L as dynamic variables, and obviously our input voltage or our input current, right? Those are the only things. So if you have something that's not in terms of EC or IL, you need a way of bringing those things together. And typically that happens through the current law, right? Typically we can do that through the current law. All right, and again, we're going to do more examples. Do you guys have any other questions, any other burning issues that you want to get covered right now at this moment? No? Everybody's fairly okay right now? Well, in that case, remember this.
We're going to talk about the operational amplifier, or op-amp for short, and this is the workhorse of all analog electronics. The operational amplifier, it's a type of amplifier. An amplifier is anything that you put an electronic signal in, and you get out a larger version of the signal. So this would be an amplifier with some sort of gain. And if I put a signal X in here, usually a voltage or a current, then the signal that comes out here is A times X. And that's what we mean by amplification. And a signal that I've shown here as X is anything that we're interested in. It could be a voltage or a current. And when we put it through an amplifier, we get a larger version of it. So this is a really common activity in electronic design. Now, when we talk specifically about an operational amplifier, the symbol for that we use for an operational amplifier is a triangle. And it has two inputs. One is the plus input, one is the minus input, and it has an output. And it also has two power supplies to it. There's some sort of plus voltage that goes into it, and some sort of minus voltage. So this is the abstract symbol for an op amp. So when we say the word op amp, we have some specific properties in mind. One is op amps have high gain. So in this case, the gain, usually with the symbol A, is something like 10 to the 5th to 10 to the 6th. Really, really high. Another thing we think about when we talk about op amps is that they're used for feedback circuits. And we'll talk about feedback in the next couple of videos and what that means. But that's the application that we use op amps for. And the third thing that's distinctive about op amps is that they have this kind of input. This kind of input here is referred to as a differential input. So an op amp usually has differential inputs, and that's as opposed to something we call a single-ended input, which would be just one wire. And what a differential input means, it says we can label the voltages here. We'll call this V out, we'll call this V plus, and we'll call this input V minus. And differential input means that V out equals the gain times V plus minus V minus. So the output signal here is proportional to the difference in the voltage between these two signals here. So I want to make a plot of this equation right here, just so we get a good idea of what it looks like. And the axes here are V in and V out, where V in specifically equals V plus minus V minus. V plus minus V minus, that's the input signal to the op amp, and we're going to apply the gain factor to it to get V out. So that'll look like this, something like this. It's going to be a very steep line, and the slope of that line, the slope of this line is A. So the slope is going to be 10 to the 5th or 10 to the 6th, something like that, very, very vertical. Now, one of the properties of this is that V out cannot go above or below its power supply voltage. So on this plot here, that's called saturation. We're going to talk about the yes, it goes flat basically here and here, where this voltage value here is minus the power supply, and this voltage right here is the positive power supply. But over this range here, over this range in here, between those 2 points, it's quite linear. It goes through 0, and this is where we use it most of the time. So now I want to talk a little bit more detail about what this symbol means here and what's inside it and how it's actually connected up in a circuit. So we talked about the voltage behavior of an op amp. This is V plus, V minus, and V out. There's one thing more that we need to know, and that is the current. This current right here and this current right here. For an op amp, An ideal op amp is 0. No current flows in here. So this op amp is just sensing the voltages at these points, but no current flows in. So this is the second key property of an op amp. The first one is the voltage behavior. V out equals the gain times V plus minus V minus. Another way we can write this is V out equals A times V in, where V in, of course, equals V plus minus V minus. So these are the two electrical properties that are going to allow us to analyze these circuits. And analyzing the circuits is actually going to be pretty simple. So you're probably wondering, like, what is inside here? What's going on inside here? So what's inside here is somewhere between 20 and 50 or so transistors and resistors, sometimes capacitors. These are really complex designs. And for right now, if we just concentrate on the two properties that we have here, we'll be able to use these circuits even without understanding exactly what's inside. Suffice to say, it's a differential amplifier with really high gain. And with just that knowledge, we can work out how these circuits work. So let me do a couple of more details on how this thing is actually hooked up. So we have a plus terminal and a minus terminal. There's more terminals on this. There's a power supply like this that's plus big V, and there has to be a minus supply, typically a minus supply minus V. And there'll be a ground pin. There'll be a ground node on here, like that. And when this is used in a circuit, there'll be, over to the side, there'll be two power supplies. And this will be 12 volts. 12 volts is a real typical value. And there'll be another one. And this is a plus 12 volt supply as well. And they'll be connected together. And this node right between them will be our ground node. That's the voltage reference. And these two guys will be hooked up like that. The two power supplies will be hooked up this way. So with respect to ground, this node is at minus 12 volts. And this node from ground is at plus 12 volts. And ground is right in the middle. And when we measure V out, we'll measure it with respect to this ground node. So this is the voltage where we measure plus or minus V out right there. And what we're going to do is we're going to assume that all of this stuff is always hooked up. And we're just going to use an even simpler symbol. Just the three terminals like that. And you'll know that all the rest of the power supply is hooked up that way. And the thing to keep in mind is there's a large minus voltage, there's a large plus voltage, and the ground level, the ground node, is right in between. So positive voltage is high on the page, negative voltage is low on the page, and V out can go both positive and negative around ground. So that's your voltage framework to keep in your head. And the op amp that we've been looking at has a symbol like this. And we know that V out equals some huge gain times V plus minus V minus. So this is a differential input. Here's V plus, here's V minus. One way I think about this is to look at the way a change in voltage on the input modifies the output. Let me label V out here. So if there's a change on the input, say V plus goes this way, because it's a plus sign, that means that V out goes this way. Now, if I change it over to V minus is on the negative input. If V minus goes up, then V out goes down. So that's the inverting, it's called the inverting input, and this is called the non-inverting input. So on the non-inverting input, up goes up, and on the inverting input, if you go up on the inverting input, you go in the opposite direction on the output. Let's say that the positive input, the non-inverting input, went down this time, And that means what? That means that V out will go down. And just do the same thing over here. I'm going to run out of colors. Let's do the same thing for the inverting input. If the inverting input goes down, what does the output do? It goes up. It goes in the opposite direction. That's a way to think about this symbol when you see it on a schematic page, is how do these signals translate through the device? Positive non-inverting signals go in the same direction. Inverting signals go in the opposite directions. Okay, and here's one final trick I want to share with you, something to be aware of. You're going to see a symbol like this on a page. The same op amp. It's the same op amp, but it's written on the page with the negative, with the inverting symbol on the top and the non-inverting symbol on the bottom. So as you look at a schematic that has an op amp in it, one of the first things you want to do is just glance and see what order these symbols are in. Or does it look like that, or does it look like that? And keep that in mind as you're reading the circuit and trying to understand what it does. Okay, let's move on and build something with our op amp.
All right. I know you guys were all super excited to watch that. Yeah, that's just what I have here, right? I just want you to be aware, right? The very last thing that he said, you'll notice that all the op amps that are in the textbook that we're going to be dealing with are going to have the negative, the inverting terminal on the top and the non-inverting on the bottom, right? And just remember, you know that you have an inverting op amp configuration. How? Well, like the one that we did last time, right? Where we got a negative output voltage, right? That means that we've got an inverting op amp, right? That's what it means. Okay. All right. So, Kat, when you say, do you need to know all of this, right? Do you need to know how op amps are configured with the power supply and stuff? Not particularly for this class. We're just going to take and use this, right? What we really need are the ideal op amp truths that we talked about last time, right? EB minus EA is approximately zero. And the current coming into the op amp is approximately zero. Those are the two op amp truths that we really need for this, that we really need. The third one is that the gain is infinite, right? But that doesn't really come into play the way that we're doing our analysis. And it really falls out as a function of the other two truths. Um, Inverting versus non-inverting, it's all about how you configure it. It's all about how you configure it, right? So like it was said in the video, right? When you have an inverting op amp, that just means that your output voltage is doing the opposite thing that your input voltage is doing, right? So if you apply a positive input voltage and you get a negative output voltage, that is an inverting op amp, right? Likewise, if you put in a negative signal and it comes out positive, right, that would be inverting. That's all that it really means. And if you look at the equation, right, where you've got the output is equal to the gain times the difference between the positive and the negative, right? Difference between EB and EA in ours, right? EB minus EA. This is just telling you that if you were to hold EB constant and increase EA, you would get a negative, you get an inverted signal. Whereas if you held EA constant and increased EB, you would get a non-inverting signal, right? So it's just inverting versus non-inverting just speaks to what you can expect your output to be. Now in real life, why is this important, right? Well, you know, you can imagine, right, if you had a sine wave going through an op amp and you wanted, right, if you invert it, what's going to happen, right? You're flipping it to basically a cosine, right? That's kind of what's happening. You're flipping your peaks. You don't necessarily want something to invert, right? But you don't always need it to not invert. It's very case specific, right? But if we know that we have an inverting op amp, we can always mitigate that as well if it's not desired. You guys have any other questions on op amps? Maybe? Really useful devices, right? They're in all sorts of things that are common to every day, right? All sorts. Typically, biggest one is a PA system, right? There's op amps in it. Very versatile, right? You can use them for filtering and amplification, which makes them really nice to use. Right? Again, the op amp itself isn't where the magic is, right? The magic is how do we set up our circuit around it. That's the magic. All right. So that being the case, there you guys go. We're gonna do our time trials for the week. Now, I just want to say this has been 3 weeks in a row with time trials, right? Are time trials the only way to get tri-quadrat points? No, no, they're not. Okay. We will do other things. It's just that time trials is the easiest thing to do when nobody's in the classroom, to be quite honest. Exam week, we'll talk about how you get tri-quadrat points that week. It is not through time trials. And next week, we actually are going to do a different activity altogether that is not based on time trials. All right, so there's that. All right, so you guys know the point structure, right? You guys know the rules. We've done this a few times. Let me make sure that the breakout rooms are set. Looks like we've got a bunch of them. Make sure we got the right amount of time. I'm going to give you guys 30 minutes to do this one. All right, you will get 30 minutes to work out this problem here. So figure 3, which is right here, has an op-amp circuit with an input voltage E in and an output voltage E out, and a capacitor C and a branch connecting output and input terminals. Derive the relationship between the input and the output voltages. Right, so I want you to create a mathematical model relating E in to E out. Okay, you guys will get 30 minutes. I'll give you 1 minute right now before I open the rooms to copy down the schematic or screenshot it or do whatever it is, however you guys like to work. All right, you guys got 30 minutes. My bad, everybody. I accidentally hit the stop button and I didn't mean to do that. So I'm going to send you right back to breakout rooms like nothing happened, right? Like nothing happened.
Makes sense. We never saw each other then.
There you go. We'll probably cut it like it's set for 30 minutes. I'll probably cut it around, 20 to 25 minutes since that's how long we were away for. And we're back. And we're back. How you guys doing? Doing all right? Maybe, maybe not.
Sure.
Right. So here we are, right? We gotta run through this one. You guys did pretty good. We're gonna roll through it now, right? So what do we got? Well, we've got our diagram first, right? So here's my circuit diagram. Okay. And what do I have going on here? Well, just so we can see it, right? I've got I1, I've got I3, which I can also call I sub C. I've got I2, which I'll leave as I2. And then what? Well, I've got this guy here, I sub A, right? Okay. And we'll call this node A because why not? Why not? So what's my input and what's my output?
En's your input and E naught is your output.
Exactly, right? That's exactly right, right? That's like, so op amps, there's no reason why you shouldn't get full points for ins and outs, right? There's like, it's always going to be E in and E out for op amps, right? That's the way it goes. So input, E in, output, E out, right? And now that we've written these as our inputs and our outputs, we need all of our equations to be in terms of these inputs and outputs, right? Because these are the only things, these are the only variables that we want to see in our equations now, right? We want everything in terms of input to output. We want a clear mapping of how we put this input in and what comes out. That's what we want. So how do we get there? Well, we're going to get there through our mathematical truths. And for this particular example, we've got our KCL at A, right? We have that node, and that node's going to have I1 is equal to IA plus I2 plus I3, right? But remember, we have our ideal op amp truths, right? So our ideal, because we have an ideal op amp, we know that IA is approximately 0. Right. What else do we know? Well, we know that EB minus EA is also going to be considered to be 0, right? In this particular circuit, what is EB? What's the voltage going into B?
Ground.
0.
Ground,
Or
right? And because of that, that tells us that EA is 0. That'll be important later, right? I also know from my element equation that this is the case and that Ohm's law in general is E sub R. Let's write it for R1, R1. And E sub R at 2 is equal to R2, I2. Right? So hey, that's where we're at. Okay. No big, right? We knew all those things. And you know what? Just for funsies, we'll rewrite this. ER, right? Because we know that we have KCL and we have to make this fit into KCL. Right? If we need to make this fit into KCL, then it's got to be in terms of the current, right? So I'm going to plug this into KCL eventually. So why don't we just write it down? Let me just write it down so we don't forget. And remember, this was also equal to I3, right? It was also equal to I3. All right, cool. So far, right? Hopefully we're all trying. Is everybody good so far? If not, speak up and let me know. It's fine.
Question for the capacitor for the CE.C. On the notes that you gave us on the first day of this topic, you also had an equation for energy stored in the capacitor, which was like E subscript CE.C.
Yeah.
Would that not be applied in this?
So we don't need to use energy to do this at all.
Okay.
We're not measuring the energy storage right now, right? There is going to be a problem that we end up doing next week where we're going to talk about why that's useful and when we would use it. But this is not that today.
Okay. Thank you.
Yeah, we don't need energy for this. Because here's what's going to happen, right? Let's go back because there's one other thing that we have to do here, right? So, all right, let's start with our reduction. Let's start with our reduction, and if we do that, hold on a second, let me make sure that's this one. So we start our reduction. We're going to start with our KCL, right? That's the only equation that we wrote down. And we have an expression for I1, I2, and I3. So we can plug those in. And then before, we'll plug those in, right? So we've got ER1 over R1 is equal to ER2 over R2 is equal to, or not is equal, plus CE dot C. And that's great, except that it's not in terms of E in and E out. So how are we going to get this in terms of E in and E out? Well, remember from class the other day, and I'm going to go back to my diagram, is I'm going to ask you guys this question again. I'll ask you guys on Tuesday, I'll ask you again today, and I'll likely ask you again next week as well. Right? I'm always going to be asking you this question. What is a voltage drop? E sub R1 is the voltage drop. What is it? What are you talking about?
The potential across a load.
Right, the potential across the element, right? So how much is coming in? We have E in. How much is coming out? It's EA, right? So the voltage drop is the difference between those two. It's how much voltage you are losing by sending it, right, across that element. So how much am I losing? Well, ER1 is just equal to E in minus EA. Well, how do I know I have EA on the other side? Well, here, it's right here, right? That's where it is. That's EA. Well, at a node doesn't dissipate voltage. The only thing that takes voltage away is it passing through an element, right? All elements have a voltage drop associated with them, but this node doesn't. So this voltage here, if it's EA on one side, then it's EA on all sides. What is the voltage drop across the resistor? It drops like that, right? So ER2 is going to be EA minus E out. Now this is the one that's tricky, right? Because we can talk about the voltage drop across the capacitor, right? And that's also going to be EA minus E out, right? But our equation is in terms of E dot, not E, right? So we have to take the derivative.
Your mic died.
My mic died? One sec.
It's back now.
Okay.
Yeah, it was back. It was a bit
Cool.
quiet for a second.
Sorry. That's weird. Ugh. Hopefully it doesn't die again. If it dies again, let me know and try something different. And just make sure I have the right mic selected. Yep, so far so good. All right. So the voltage drop across the capacitor is EC is equal to EA minus E out, right? But our equation isn't in terms of voltage drop, it's in terms of the derivative of the voltage drop. So we have to take the derivative of this EC, right? If I take the derivative of this, it just becomes that. Right? So again, first of all, if you cover up the capacitor branch here, right? This is the same problem that we did in class on Tuesday, right? So logically, right, wouldn't it make sense if the answer looked just like that, but with the capacitor portion added to it? Right? Logically, wouldn't that make sense? And that's so we kind of have an idea of what the response here should look like, right? I don't have that.
Dr. D,
Yeah.
why don't we write in the truths what ER also equals like what you just wrote, like ER equals EN minus EA?
You can if you want. I didn't because I wanted to show you on the diagram.
Okay.
I'm not, so in my mind, right, if you don't have that in the truths, I'm not gonna fault you for that. It's fine. You can if you want, if you're concerned that you're gonna forget about it. I think it makes more sense personally to talk about it on the diagram. Right? And if I had written it down, I wouldn't have been able to ask you all those questions and try to hopefully lead you guys to get the answer there instead of just giving you the answer.
Right. I'm just thinking in terms of doing the problems
In terms of
substitution
doing
wise.
and getting grading, right? I'm not concerned with that being in the truths. That's to me not something that's an algebra step. It's not something that's driving the system, right? That's I guess the difference in my head about it.
Okay.
All right, so if we come back here, we can incorporate what we just did, right? So we can have the voltage drop here, we know is EN minus EA over R1. We've got EA minus E out over R2. And we've got C times E dot A minus E dot out. So let me ask you the question here, right? We know that EA is 0, right? What is the derivative of EA equal to?
0.
It's also 0. Derivative of a constant is 0. 0 happens to be a constant, so hey, 0. So hey, look at that. Now everything seems to be in terms of our other variables that we were interested in, right? Sorry, that should be a minus, not a plus. Minus the dot. Right, and just to clean it up a little bit, I'll rewrite it as C E dot out. Sorry, as R2C, R2 times C E dot out. So I'm going to multiply through by negative R2 plus E out equal to negative R2 over R1. So I'll just algebra. What if you left it like this, right? You left it like this, I'm fine with that too. I just think it looks nicer when you clean it up like that. There's also a specific reason why I cleaned it up like that we'll talk about when we get to talking about the standard form for a first order equation, which we're not there yet. So, but just understand that sometimes the way that you write things, so kind of like coordinate systems, right? You can do anything with any coordinate system, right? But some coordinate systems are better than others, right? Because they make your life easier. The way that we write certain equations sometimes matters in the sense that it will allow us to pull information from them at a much faster clip. And you'll see what I'm talking about when we talk about standard form of first and second order equations.
Doctor, do you have a question?
Yeah.
On the example you did on Tuesday, you had E out was all by itself. And so I'm guessing the question I have is when we do these equations, what is it the primary thing we're solving for?
You want to have your inputs isolated from your outputs. That's
Okay, that makes sense.
So again, look at this, the way that I wrote it in the black box here. If you
Yep.
cover up the capacitor portion of it, it's the same exact equation that we had
From Tuesday.
right?
Yep.
We just have that capacitor part added. So again, it's all about just trying to isolate our inputs and our outputs, right? That's what we want. That's what we want.
Okay, thank you.
Any other questions? Awesome. Any other questions? Everybody doing okay? We're gonna jump off of op amps now today. you have any other op amp related questions, you can always ask me, office hours and things. There's definitely an op amp question on your homework, right? So take a look at that, right? I didn't say this at the beginning of class, but I'll mention it now. I'm almost done grading the lab reports, and I'm also working on the homeworks simultaneously. So hopefully the lab reports will get done today, and then the homeworks will be done probably over the weekend at some point. If I'm being honest, it'll be done before Sunday, so you'll get them probably Friday or Saturday, hopefully Saturday, but we'll see. Definitely get them back before Monday. Cool. Any other questions? Now we're going to talk about some fun stuff. He said, and nobody believed him. Right. Let's talk about some fun stuff, right? Change it up.
Dr. D?
Yeah, what's up? My mic
No. For these problems on a test, in terms of like drawing the free body diagram for these, can we just like, do we not have to duplicate the same drawing? Can we just start doing the input and output?
I would definitely annotate the circuit diagram. You don't have to redraw the entire circuit diagram, but use the one that's there and make sure that it has everything on it that you need to write your code.
Okay, makes sense.
Right, so they're helpful for, if you had to do KVL, making sure you have the right loop pointed out, right? If you have to do KCL, which node are you talking about, right? So definitely annotate your diagrams. All right. Ethics paper due on Sunday, homework due a week from Sunday, exam 1 on the 8th, and homework 3. Homework 3 on the 11th, right? Just so you guys know, what's going to happen is next week on Tuesday, half of you will be in class, so that's most excellent, right? On Tuesday, we're going to tie a bow on electrical and electromechanical systems, and on Thursday next week, we are going to jump into thermal and fluid systems. That is the plan. I know the hits keep coming, right? The hits keep coming. And the greatest hits, GCU greatest hits.
What's your setup going to be when you're teaching to half virtual, half in class?
This same exact setup that I have.
Looking at the screen like this, or kind of both?
Got it. So it's still gonna be Zoom. I have a tripod. I might set up a camera in the middle of the room and walk around a little bit more, but for the most part, it's gonna be screen share. For people on Zoom, it's gonna be screen share and a camera. And for people in class, you're gonna have to deal with me yelling because I'm gonna have to wear a mask, and so I'll be louder than this. So.
Right. I was gonna say, I hope we can hear you.
So yeah, I'm sure we'll have to tweak it a little bit, but we'll see what works. And if it's not working on Tuesday, we'll adjust. All right, so electromechanical systems, right? Electromechanical systems. What are they? This is the part where, remember I told you last week, I don't like when you say, well, it's an electrical and a mechanical system that you put together. Right? And yes, that's true, right? Yes, that's true. But what actually is it, right? What actually is it? What is it meant to do, right? It is meant to convert some electrical input into a mechanical output or vice versa, right? Or take a mechanical input and create an electrical output. So what is a real world example of an electromechanical system? Anyway.
Garage door opener.
Sorry, say that one more time, James.
A garage door opening.
Sure. As long as it's an electric garage door, right?
Yep.
I mean, my grandfather's old steel garage door doesn't open itself. That's why he had so many kids. So, anyway, all right, yeah. So like garage door opener, right? Sure. definitely electromechanical system. You take some electrical input and it creates a mechanical response. What about the other way? Let's go the other way. What's a device that takes a mechanical input and gives me an electrical response?
A generator.
Generator. Exactly. Right? Rev the generator and you're just running, it's basically a motor that you run in reverse, right? It's just basically a motor that you run in reverse. I realize that is grossly oversimplified. All right, so I mean, we talked about a little bit about applications and examples, right? We've got motors and generators, right? We've got actuators, right? So if we want, you're thinking about robotics, right? How do we get our robotic arms to move? We have actuators in there, and actuators, anything that instigates a movement, right? We've got sensors, right? Strain gauges, accelerometers, speakers and microphones. That's another fun case of a speaker and a microphone are just the same thing, but run in opposite directions, right? So by combining mechanical and electrical elements, we can make a variety of useful electromechanical devices, right? And I think you guys would all agree that we use electromechanical devices in many of the facets of our daily lives, right? Here's the definition. These devices convert electrical energy into mechanical or mechanical into electrical, right? They are specifically used to convert energy from one form into another. And they exploit the connection between current and magnetic fields to produce a mechanical force. And so they obey Newton's laws and Kirchhoff's laws at the same time, right? That is super exciting. It's super exciting, right? Because you guys thought like, you know, I really like Newton's laws, but I could go like either way on Kirchhoff's laws. But Kirchhoff's laws, man, they're here. Don't go to Kirchhoff jail because you broke the Kirchhoff laws. I mean, that's a horrible joke. Why would you say that? I don't know. I don't know why I said it. All right. So how do we characterize the current magnetic field interaction? Right. There's a few things here, right? And we can use Faraday's laws to talk about this. Right, so there's three basic relationships that we're going to exploit here. First, that when we have an electric current, we can establish a magnetic field, right? So basically having a current run through a wire will establish a magnetic field on its own. The second is that a current carrying wire that is already in a magnetic field will have a force exerted on it. So if you have a wire that has current and you put it in a magnetic field, there's going to be some force. Why? Well, because of the first one, right? You created a magnetic field, and then you're having this magnetic field interact with yet another magnetic field, right? So if it has the same polarity, it will repel, and if it's opposite polarity, it will attract, right? Third, a moving wire relative to a magnetic field will have voltage induced between the ends, right? So if I move this wire, right, through a magnetic field, I'm actually going to induce some voltage in it, right? Interesting. So let's talk about this, right? So the Biot-Savart law describes a magnetic field B. And guess what? The magnetic field operates using the right-hand rule, which tells us a little something about it that we're not going to really talk about too much, right? But what is the right-hand rule in this case, right? So the direction of the field lines is defined by applying it. What do? Well, we place our thumb. If you're holding the wire, you place your thumb along the direction of current, and the way that your fingers are curling determines which direction your magnetic field runs in. Okay. Now, I told you that because this deals with the right-hand rule, right? This tells us something. Well, it tells us what? Well, it tells us that the magnetic field is what? Magnetic field is the cross product between current and something else. Right? How do I know that? Well, it's perpendicular to those two things. That's what the right-hand rule would tell us. And so that's important information because that defines B for us, the strength of our magnetic field. here's the second one, right? A current carrying wire in a magnetic field has a force exerted on it, right? So if I have this wire here, right? I've got my wire here. That didn't work. I got my wire here, right? And I've got some current flowing through this wire. What's L? We'll talk about L in a second. And there's a magnetic field traveling from north to south here. Well, then there's going to be some force acting on this, right? So for a wire perpendicular to a magnetic field, we can reduce this equation, right? We can talk about it in terms of a scalar instead of a vector. So if we're good about how we position our wires in a magnetic field, we can simplify the math, right? And so the force is just B times L times I, where B is the magnetic flux density in Weber per square meter, or some people call this a Tesla. So, there's that. L is the length of the wire. So how long my wire is depends on how much force will be exerted, right? Why? Because this is going to tell us what? Well, it's going to tell us how long our field is, right? It tells us how long our field is. What's I? Well, I is the inductance. No, I'm sorry. I is the current. I don't know why I said inductance. Dr. G's brain is not working. Not working today. I is just our current. So we've got B times L times I, right? Magnetic flux density times L times I. So it's the amount of force that we have exerted on this wire is dependent on how strong our magnetic field is, how long our wire is, and how much current we send through. I think this makes sense, right? If you've ever played with an electromagnet before, right? The more current you give it, the stronger that force is going to be, right? The more current you give it, the stronger that force is going to be. The stronger the magnetic field is, the stronger that force is going to be. The one that's weird is that the length of the wire, right? Well, remember, the length of the wire determines this, also determines the size of our field, right? So that's important. You might also even see this with an N in here, right? What would the N indicate? The N indicates the number of curls in a wire, right? The number of turns. If we have something like a inductor. You guys okay with this idea here? That if I have a current carrying wire in a magnetic field, there's some force exerted on it, right? We should have at least heard of this before in physics 2, in 122. And lab. Is that okay? Is everybody following so far? Any questions so far? All right, so level in with you guys. Magnetic fields for me are one of the hardest things to deal with, right? Because I am a very visual person. One of the reasons that I decided to go after a mechanical engineering degree was because I could actually see how things interacted, right? This magnetic fields are invisible and they're hard for me to visualize in certain cases. So I get it. But the result is the same. If you have a magnetic field, that field is exerting some force on this wire, right? Because they have interacting magnetic fields. That is why. Because they have interacting magnetic fields. All right. A wire, so if I'm moving a wire through a magnetic field, right? I'm going to move this wire through a magnetic field. It has the same voltage induced between the ends of the wire. Or not the same. It has a voltage induced between the ends of the wire. We're going to call this is a special voltage, right? So imagine I have the same wire. Now notice we don't have any current flowing through this wire, right? This is just a wire. And we're just going to pull it up through this magnetic field. Well, if I pull it up through this magnetic field, it's going to create a back EMF. It's going to create a back EMF, right? There's going to be some voltage that flows through here that's fighting against if I was to start a battery. All right, if I was to hit a switch and turn it on. How do we discuss this? Well, the back EMF is what? It's the voltage cross the magnetic field dot L. Well, we're going to simplify it. We're going to say, well, for something that's perpendicular to our field, then this back EMF is just B times L times V, right? Where V is the velocity of the wire, L is the length of wire, and E sub B is my back EMF. So, all right, so this should come out in volts, right? Should come out in volts. Interesting. Interesting. So again, the faster I move the wire, the stronger the back EMF. The stronger the magnetic field, stronger the back EMF. And the longer the wire, the stronger the back EMF, right? So that's all great, Dr. D. We've got these two, this equation for force and this equation for back EMF. Well, I want you to look at this equation for force again for a second, right? Because this is a big idea. You can generate a physical interaction with the world from nothing other than current, magnetic field, and a length of wire. Current and magnetic field are completely electrical concepts, right? But we're now interacting with the physical world. This is the bridge. This equation bridges for us the electrical world and the mechanical world, right? And this is the key. This is what's going to allow us, right? And this one as well, because this is a function of velocity. This is going to allow us, these two equations, to have electrical systems that affect the physical world, right? So let's learn a little bit about motors from my main man, Mr. Wizard.
That's my homemade motor based on wire on cotton. Isn't that weird?
Weird.
Weird. Isn't it weird? It looks like an ordinary motor to me. But that's your word for great, good, or something weird?
Yeah.
Okay, I'll accept it as a compliment. You can build one of these yourself, out of stuff you can sort of find your own house. But first, I think you should make sure that you understand the principle of what makes a motor work. See that magnet over there?
Yeah, this one?
Right. Well, this one's sitting on a turntable, so it can spin around. If you bring the north pole of one magnet near the north pole of another, wow.
It repels.
Yeah, repels. Then you see this turn, you can now bring the south pole around like that, it's going to give it another spin. And then the spin, see if you can get it there. That's the principle of the motor. A spinning magnet, and one that you can change polarity.
Right.
And when you can get them in the right sequence, why you can get the other one to spin. Okay, let's now take a look at this one, because this is a sort of a real motor. You want to put that over there? This time, the current's going to come through here from my power supply and go through there. What will not make that?
That'll make it into an electromagnet because there's a lot of coil wires, and when an electrical current goes through lots of coiled wire, then it makes it into an electromagnet.
And not only that, but see how this is curved around out here, the magnetism is going to come up. This is all going to be conveyed. So is that.
Okay.
Then here, I'm going to use my paintbrush as a pointer because the important part is going to be kind of hard for you to see, and I want you to be able to see it. First of all, the easy one. Where is the magnet to spin?
Right, over there.
They're electromagnets too, they're coil wires.
Right.
Now, what does the word commute, you know?
I mean, it's like somebody that gets on a train and goes to work and comes back.
Goes back and forth, back and forth. Well, it's just the same root of the word, but it's called a commutator in this case. The thing that reverses the polarity. You see this right down here, the shiny part right there?
Mm-hmm.
Okay, there's a little piece of metal that rides against that, so current can go through there and make it into electron. Now, see it goes through a slot there?
Mm-hmm.
Okay, now it's making contact with this, and that makes this into a magnet.
Right.
Then the next one comes around, there's one by the slot, and that makes, now you can make this into a magnet. So that's reversing the polarity, and that's why it's called a commutator. All we have to do is add a little current.
And turn on.
There you go. Now see if you can find the important parts of the motor right here, because this is from an actual real motor, but I took it apart so that you can see the important parts. First of all, where is the spinning? Right.
They're the ones that like, yeah.
Right down here.
And then there's the close wire.
Then, here's the commutator in this case. See that little black thing right there?
Mm-hmm.
That's a carbon crusher, a hunk of carbon. Current can come up through here. Now the carbon touches this part right here. Current can come up on the other side and touch that one over there. So that's how the current is reversed, as this spins.
Okay.
Okay? What's missing?
The stationary one.
Okay. There's one right there. I'll turn on the current. You hold this magnet up above.
Wait, they can feel the electricity. Alright, let's get away.
Okay. Now that you know all the important parts of the motor, come on over here and see if you can just figure out how to build one of your own.
Okay. First of all, you need the stationary magnet that's down there.
Ground magnet down below.
And then you need the electromagnet, the ones that
The
spin.
spinning magnet, that's gonna spin right there.
Yeah. And then there's like sort of electricity, right? And then there's wires that come up. And then
What's missing?
the commutator.
Yes. Certainly, this is a very clever thing that my friend Bud Lynch put in there. See that wire down there?
Mm-hmm.
Well, part of it's dark. See how it's dark on one side?
Mm-hmm.
That's enamel, which works like an insulator. But you scrape off part of it, so when you turn it the other way, you see how it's scraped off and it's shiny?
Mm-hmm.
That means current can flow whenever the shiny part is touching the top of this into the safety
Because
pin.
of the pulse.
So yeah, current can go through and give it a pulse. It goes down and to the other side. Then when it's like this, no current goes through. Then when it comes around again, current goes through. So that's the secret of this homemade motor. And I cannot see if it will actually go.
There's just.
Right. With a little stereo.
Hey.
So you could make your own homemade motor with a permanent magnet, a coil wire, a safety pin, and that.
I'm gonna make one of those at home.
Yeah.
Aren't we all? Aren't we all gonna make one of those with me? Sweet, right? So what are the parts of a motor? We just saw Mr. Wizard talk about it. What do we got? So for a DC motor, right, it's important to we're gonna bring that up. We're talking about DC motors now, right? We're not gonna cover AC motors in this class, right? We're gonna strictly talk DC motors, right? So a DC motor has what? It's got an armature or a rotor, right? You see it here, armature, the rotor is the central piece, right? And our magnetic field is generated or is established by the stator, right? So the stator is our stationary magnet. The armature, right? The armature is a rotor with windings on it, right? So that's our central in the example that Mr. Wizard showed, right? That's the rotating electromagnet that we're creating. Okay. Right, so the armature windings in the top half of the rotor carry current flowing into the page, right? While the windings in the bottom half have it flowing out of the page towards us, right? So we have some on the top, we've got some current flowing into the page over here. Right? Imagine for a second, right? And down here, it's coming out of the page, right? Why do you draw it like that? Well, it's how people draw vectors, like in and out of the page in 2D, right? Think about it this way: if a vector is an arrow, then it's got fletches on the back, which look like X's if you're looking from behind, and from the front, you would see the tip. That's what that is. We have a radial magnetic field here, right? So our magnetic fields are intersecting in a strange way, right? It remains perpendicular to the armature windings, and therefore the induced force on each individual wire is tangent to the rotor's surface. So we can write this down, right? The total electromagnetic torque on the rotor, we can write that down. Right? So the torque of the motor, T sub M, well, remember, a torque is what? It's a force times the distance away from our axis of rotation. In this case, F times R. But F, we talked about what F was. F was B times L times I, right? So R is the rotor's radius, and L is the total length of wire used for the windings. So B times L times I times R. So I have a torque now, right? That's very useful, right? Because if I have this equation, right, then I can figure out how much motor torque I generate. And I think that if you've played with a motor before, I think that this equation makes sense. Because the more current that you give that motor, right, the more current you give that motor, what's going to happen? Well, you're going to increase that force, right? You're going to make it spin faster. Make it spin faster. So typically, when we are using motors, though, we don't talk about B times L times R, right? We lump these all together into something that we call the motor constant, which is going to be capital K sub M. So B times L times R is K sub M. So we can rewrite our torque as Tm is equal to Km times I. And this is the motor torque constant, and it has units of Newton meter per amp, right? When you go and buy a motor, you will be told what the motor constant is, right? You're given a performance graph that gives you the slope of the line that tells you what K is. Okay, that's what it does. It shows you how much torque you can expect given how much current you put in, right? So the slope of that line would be K sub M. Solid, right? So the larger K sub M is, the more torque we get out, and the larger I is, the more torque we get out. Okay. Remember, B, L, and R, these are all design specs, right? This is the stuff, like if you're going to size a motor, right, you want to know what K is, right? You want to know how the current, what range it's used to perform over, right? What is my max torque? How much current can I give it? All of those things. Likewise, right? So remember what a motor is doing, right? So we've got this wire, it's carrying a current through a magnetic field, right? And because of that, we have a force on it which produces a torque, right? Fine. But the motor is also causing that wire to move with some velocity through our magnetic field. So it also produces a back EMF. What is the equation for back EMF? That's B times L times V. But from dynamics, right, we remember that the velocity at the edge of this, right, this velocity is just a function of R times theta dot. So as it turns out, we'll get B times L times R times, well, B times L times R, that is, isn't that just the motor constant? Well, yeah, yes, it is. But we're gonna call it K sub B in this equation. But it's just the same thing. It's the same values. So our back EMF is K sub B times theta dot. So the faster that we spin this, the more back EMF we are generating. And the back EMF constant has units of volt second per meter. Oh, I'm sorry, volt second per radian. You can do the unit conversion. You can check to see that these are equivalent, right? And here it is, right? 1 volt is 1 kilogram meter squared per second cube amp, right? Which is 1 Newton meter per second amp. So there's that. Okay. You guys have any questions on this, right? The equations in purple are important. They're important, right? That's why they're purple. That's why they're purple. In the real world, are you going to have to worry about B, L, and R? No, because you're going to have the motor constant, right? And it looks like the motor constant is equivalent to the back EMF constant because it is, just has different units, but those units are equivalent, right? Those units are equivalent. Okay. Does have any questions? No, not right now. Doing okay. All right. Well, if we're doing all right, let's watch another video. This one is actually going to talk about how an AC motor works, right? But it's a similar principle to the DC motor, and it's an interesting video. So let's take a look. All right. You guys all in on electric cars? Yeah. You think they're going to replace internal combustion vehicles?
Yes.
Yeah, the answer is no.
Yes, but it will take a while.
It's not going to be, yeah, it's going to be a while. So,
Hey,
Electric transportation will. I don't think that we'll see cars at some point. I think we'll see a lot of heavy automation replace the transportation industry.
Also, the battery pack is not there for stability. I don't know why that person said that. If you are designing so that your batteries are part of your stability structure for your vehicle, that is an issue, right? So that just please don't think that that's the thing. All right. Anyway, so let's run through some example problems. We got a little bit of time left today. We'll probably get through one. We'll probably get through this one. So my sheet says Josh Denton. You're up. What we got? So let me just ask you this, right? When you guys see this, well Josh is getting stuff. When you're looking at this, you guys think, holy crap, I have no idea how to do this. Like, show of hands. Who is overwhelmed by this right now? Anybody? I can't see everybody on here, so I don't know why I asked for show of hands.
We all are.
Okay, well, break it into pieces, right? You've got a circuit on one half, and you've got a rotational mechanical system on the other. Just do it as two separate pieces and see what happens, right? See what happens. All right, so Josh, I'm gonna give you the main stage here.
Do this the easier way. Put some extra light. There we go. So this is terrible lighting. So I have the circuit of that, and I did the excuse me, separation. So I have IL in the upper left. It's kind of hard to see because the lighting sucks in the corner of my room. Then I separate it using 1 and 2 just to help keep it straight for me. And then the camera does not like to focus. Yeah, that's not too bad. So this is TM.
Right.
I have theta going to the right. I have my TB at the bottom, going opposite of theta, and TL going opposite of theta.
Right.
So my global input, I have EN, and output, I have TL and theta.
Okay.
And then I have separated my mathematical truths just to help keep them in line. I have EL equals to L I dot L. Then ER equals RIL. Then EB equals KB theta dot. That's all for the electrical system. Electrical part. And then at the mathematical truths for the cylinder. So the sum of the torques equals J theta double dot. TB equals B theta dot. Then TM equals KMIL.
Mhm.
And then I have the reductions for the electrical system. I have EN minus EB minus ER minus EL equals 0.
The KVL, right?
Yeah.
All right, it's kind of tricky to read.
Yeah.
So I'm gonna switch back. I'm gonna start writing on the screen, but good stuff, man. Good stuff. And your thoughts on how to break this up is good, right? And it's good. It's a good practice for you guys to get into, right? Is look at each of these piecewise, right? Reduce just the circuit, reduce just the mechanical system, right? And see what comes out. The one thing I will ask you guys, right? So, all right, so let's start here, right? Let's start with how Josh started, right? We got to draw our picture. So what do we have? We've got our circuit here, right? And this is a simple RL circuit, right? Well, simple-ish, because it has this back EMF that we haven't really talked about yet in class. Right? And this is LA. Notice the subscripts RA, LA. What do those mean, right? Well, technically, we are analyzing the armature circuit. This is the armature circuit for our motor. Okay. Now, what's going to happen is we're going to give it some voltage, right? We're going to give it some voltage, and it's going to run through our circuit. And that's going to create a magnetic field through our inductor, which is a bunch of coils of wire, right? And that magnetic field is going to interact in some way with our mechanical system, right? And so our mechanical system has a free body diagram here. It'll be in blue, right? Because I forgot to switch colors, but that's fine. We can deal with this, right? I chose theta this way. It doesn't matter which way you choose it. The picture actually draws it the other way, but for the sake of my notes and me not losing my sanity, we're gonna do it this way. Does it matter? No. And here's why. Because I am drawing the torques in the same direction that you would have them if we were going the other way. Okay. So I've just split my signs. That's it. Okay, so what's TB? TB is my damping. How do I know that there's damping there? Well, I've told that there's viscous friction, so we're going to assume that there's damping. What about TL? What is TL? They call it out on the drawing as a load torque. What is a load torque physically? All right, so you've got a motor, okay? You've got a motor. Yep, see, motor. You guys heard it. It was there. So you've got this motor, and it's attached to something, right? It's attached to some system. It's attached to a flywheel. It's attached to something, and that something has some mass associated with it, right? In order for you to get your motor to start, you need to overcome the load torque. You need to overcome the inertia of whatever it is attached to. Think of it as almost like, yeah, it's like having a flywheel attached to a motor, right? That flywheel has some weight associated with it. You need to produce a certain amount of torque to even get it to start moving, right? What is that? That's our load torque. Right? Now we have a couple of equations here that will help us jump back and forth with magnetic fields, right? Doesn't need two of those. So what do we got? Right, well, we know that magnetic fields are going to, all right, so before we move on to that, right, let's look at this circuit, right? This circuit's got that back EMF, and we've drawn that back EMF as what? We've drawn that back EMF as a source, right? That's a voltage source here. Right? That's a voltage source, and I'm going to draw this because there's no nodes here. So I'm going to assume that I'm going to have to use KVL because there's no nodes. I can't use KCL here. It would not make sense to use KCL here. Okay, great. So we got this. More on that in a second. Let's go and talk about our inputs and our outputs, right? So Josh made a claim, right, that E in is our global input, right? Remember, we're talking about the idea of global input being the one that starts everything off, right? So if I have a motor, I give it some voltage, I give it some current. That's what is starting this, right? It's the overall input to my system. What are my outputs then? My output is my load torque and theta. I have two outputs. Two outputs. So it's my load torque and theta. Okay. All right, so far so good. Is everybody following me? Just general inputs and outputs, right? Again, what is the input? The input is the cause. What happens? I give some voltage. Okay, what happens as a result of that? My motor starts to turn, so I get some displacement, right? I also have some load torque that I need to overcome, so that needs to be part of that output. It's going to actually, as we'll see, it's going to actually decrease the amount of usable torque that we have in our system. So what about our truths, right? And this is where we're going to separate them, right? I'm going to have my electrical system truths here, right? And this, I think that this is good practice to get into because you're going to isolate each one of these systems and then you're going to analyze each one of these systems, right? So what do we have? Well, I know that I have some force, we'll call it FEM. Actually, no, we're not going to go there. We know that we have some motor torque, right? We're going to identify motor torque here. And that seems like a weird place to put it, right? Because that's not really part of my, actually, I'm sorry, we're looking at the, we're going to talk about EMF first, back EMF. There we go. Now Dr. D's on the right page, right? We define this as BL times V, right, times R, right? Which is B times L times R times theta dot, which is just going to be KB theta dot, right? We went through that on a few note slides ago, right? KB theta dot. Okay. We wrote down our KVL, right? But remember, we've got a resistor, so E sub R is R. I'm going to call it IL, and E sub L is equal to L, I dot L. So we have an inductor. What else do we have? That should be it for my electrical side, right? So I can write KVL here too. So minus E sub R, minus E sub L, right? Minus E sub B plus E in is equal to 0. And so we go back. Why is that the case, right? We go back. Well, if I'm going around the loop this way as I've drawn, I have a voltage drop across my resistor, I have a voltage drop across my inductor, I have a voltage drop across my back EMF, and I have a voltage gain across my source. Okay. I'm going to put my mechanical system truths down here. First and foremost, the sum of my torques is equal to J, theta double dot. I also know that I have a damper. My motor torque is KT or KM, depending on. So you will see KM and KT used interchangeably, right? The motor constant, torque constant. That's what we have there. That's it for us, for mechanical system. Yeah. So which one do you guys want to look at first in the reduction? I'll give you the choice, electrical or mechanical.
Electrical.
Electrical, alrighty. The electricals have it. All right, so let's reduce this, right? Electrical system. This circuit. Remember, negative ER minus EL minus EB plus EA equal to 0. Okay, well, this is just negative RA times I sub L from our Ohm's law. Lots of work going on. You guys aren't even going to recognize it on campus when you get here. So much work going on right now. And they waited until today to do it, which is awesome. I'm really, really happy and excited about it. EL is LA I dot L. EB is what? Well, we define that, right? That's KB theta dot. And we're going to leave E, we call that E in. Sorry, not EA. Apologize, that's E in. Okay, we don't change the variables. So I can rewrite this. I can rearrange this, right? And it's got E in is equal to LAI dot L plus RAIL plus KB theta dot. So hey, look at that. I've got everything in terms of IL, E in, and theta dot, right? Remember, for an electrical circuit, we want everything in terms of E sub C or I sub L. But look, now we're coupled. We're now coupled here, right? We're coupled to our mechanical system. And that's fantastic. Because if they weren't coupled, then this wouldn't be an electromechanical system. Is everybody okay with the reduction here? Did we follow with the circuit, right? It was a pretty standard circuit. Is everybody okay? Do you have any questions so far? Any questions so far? No, we good? All right. So what about this mechanical system? What about this mechanical system? Now, Josh, mine might look a little different than yours because I flipped my direction, but that doesn't mean that you guys are wrong. It just means that I have to grade it with your coordinate system, right? So as long as you put your coordinate system there, then it's fine. All right, cool. So what do we have to do for a mechanical system? We need to do the sum of the torques, right? And if we look at our free body diagram, which I will let you guys look at yours instead of going back, right? What do I have? Well, I've got the sum of the torques is going to be the motor torque, right? T sub M minus the load torque minus the damping is equal to J theta double dot. Let's actually write theta instead of something that looks really gross. J theta double dot. All right. So we can rearrange this a little bit, right? J theta double dot. I'll bring my TB over and substitute in B theta dot. And this is going to be equal to my motor torque, KT, times I sub L, minus my load torque. My input to the mechanical side of the system is technically the current, right? The more current I give it, the faster it's going to want to go. Now, this is interesting, right? This is interesting because, like I said, that load torque eats up the amount of usable torque that you have, right? And so if you give this just enough current so that you have not broken TL, you will not spin in the right direction, right? This is what this is saying, right? This is what this is saying. All right, so that's it. We leave it there. Do not try to combine these. You're going to give yourselves a lot of headache and a lot of heartache for no reason at all. Leave them. Leave them as two separate equations. Just leave them. Typically, in the real world, we are less concerned with motor position, right? We're more concerned with the velocity. That's just, functionally, it's a better quantity for us to have. So how can we change the dynamic variable here? Well, if I take my first equation, En equals the En minus, well, this was KB theta dot, right? I'm just going to change theta dot to omega. Similarly, I can change all of my thetas, my theta dot to omega and my theta double dot to omega dot. Because there's no spring here, this is a very nice looking equation. And so this right here is just us changing the dynamic variable to talk about something that has a little bit more real world use. How fast is my motor spinning? Spinning by omega. All right. Any questions today? We're gonna wrap it here. Yeah, we're gonna wrap it. I'm hoping that you looked at that mechanical portion and you were like, I get that. We covered that. That's a simple mechanical model. I can see where that came from. The electrical system, I understand. There's trepidation there still. We're just gonna practice more. Next class, we're gonna do more example problems. We'll talk about a couple other things having to do with MEMS, right? But for the most part, we're just gonna do examples, more examples next class. Tie a bow on electrical systems on Tuesday. Thursday, we move on to thermal fluids. Okay.
Hey, Professor, I have a question about that last problems you did, the ones you highlighted in blue or dotted
Yeah.
in blue.
Yep.
What did you say that one was for again? In terms of, other than power?
The angular velocity instead of the angular position.
Okay.
Right. So when we get to talking about how things respond in the real world, nobody's ever, and I mean this, nobody will ever come up to you and say, what is the position of the motor? Right? That's not a thing that people care about. People care about how fast it's moving, right? Which is the velocity. So all we did was change the dynamic variable from theta to omega, which is our which is from angular position to angular velocity.
Got it. Thanks.
So we're gonna call that one. I'm trying to get to my last slide here. We have a lot more problems that we're going to work on next week. Oops. No. All right. Any other questions before we tie class up? No. Well, because it's kind of like Friday, right, I got bad news for you. This is Dr. D's Deep Thought for this week. Here's my bad news. Well, I don't know. You guys be the judge, right? If you had $1 for every year that the universe existed, you would not even make the top 50 richest people in the world as compiled by Forbes last year. Now, I understand that this is in hot debate, right? So this is an estimate. an estimate. You would, however, be in the top 90 richest people in the world, right? So that's, I mean, that's pretty cool. Considering that there's 7.53 billion people in the world, that would technically put you in the top 0.0000001% of richest people in the world. So good job, everybody. Good work. Oh. Smiley face. That's all I got for today, guys. Here's the thing. Please fill this out. There will be one more after this, so let me know how you're doing. Again, I said it last week, I'll say it again this week. If you're feeling towards the red side of things, please, please, please come seek me out in office hours. I am not a mind reader yet. I'm working on it. It's just not, it's not there yet. So if you're having problems, you need to let me know so I can help you. I'm here to help you. I want to help you. I want everyone to succeed. Please let me know if I can help you. And then I'll leave this here and you guys can fill it out. When you're done, just head out. All right. Have a great weekend, guys. If I don't see you in office hours tomorrow, right? Remember, try to get your work done. That's important, but it's also important that you reset a little bit. So, you know, do something for yourself as well this weekend.
Thanks, Dr. D.
No problem.
Thank you. Have a good one.
Take it easy.
Have a nice day, Dr. D.
You too.
So I don't know what it is, but like internet where I am right now is like super, super rough. So during the entire lecture, it was like, so I probably got like a quarter of what was going on. So
Okay.
I'm gonna try to rewatch the lecture and stuff tonight so that tomorrow afterwards I can like have.
All right. Yeah, I think I got most of that.
It was mainly like the electrical like equations was rough. It was a rough one today.
Yeah, I imagine that this is not ideal with when your internet's not